All right, so now we're taping. Actually, before I get into these 7 pages of notes, I know it's quite a tease on my part, but I still have a little bit of material left over from exponentiation of Jordan forms. I have to do a complex case, and then we'll dig into those final 7 pages of notes. Okay. So this is really like a subset of 6.2, and then after I finish this, I'll get into the regular stability material that chapter 6 is about. So just a quick recap. So A is expressed in terms of its Jordan form, and we really care about the matrix exponential, which just involves exponentiating the Jordan form. And J is a block diagonal matrix of Jordan blocks. So the exponential of that is just the exponential of those Jordan blocks individually. Okay. And these Jordan blocks are either real or complex. So real Jordan blocks is what I did the end of last time.
I'm passing gum.
Oh, okay. As I turned to like noises.
Yeah, it was gum.
Okay, I was laughing.
Does anyone else want gum?
Thanks.
Where's my cash?
He already has some help.
It's an hour and a half long.
Reminded of something.
Okay. So this is a K by K real Jordan block, and the formula this turns out to be e to the lambda t. Well, actually, it's just e to the lambda t multiplying everything out front. And then
That's a J times T, right? E to the JT. Go over matrix. Yeah, E to the JT.
yes,
Okay. Just confirm.
okay. And then we have 1 along the diagonal, and t, and then t squared over 2, and so forth, all the way to t to the k minus 1 over k minus 1 factorial. So that's how we do the real Jordan blocks. And this is good to keep in mind because I'm about to do the complex Jordan block, and it's going to be similar. All right. So, first, to refresh memory, is to the form of a complex Jordan block. Now, I guess maybe calling it a complex Jordan block is a bit of a misnomer because the actual matrix involved is going to be real. However, it corresponds to a complex conjugate pair of eigenvalues. So since the eigenvalues are complex, that's why I'm calling it a complex Jordan block. And I'll use this notation, C2m of AB. All right, so we have blocks C of AB along the diagonal, and these are 2 bits of matrices that have A on the diagonal, and then plus or minus B on the off diagonal. So the eigenvalues are A plus or minus I. And then we have above it 2 by 2 identity matrices. So we have this block upper triangular structure, and everything else is 0. Okay. Now, what we can do is break this down. So what we did in the real case was we wrote this real Jordan block as lambda times identity plus this matrix that had these ones, which is a nilpotent matrix. And we can do a similar thing here. We can decompose this as, write it as D2M AB plus, call it big M. So everything here is 2M by 2M matrix, where M is the multiplicity of the eigenvalues, but we have 2 eigenvalues, so the size is 2M. Okay, so this is block diagonal. And this is, so this is nilpotent. Okay, so now I'm going to show you what these two parts are, and then what we can do to them in order to compute the exponential of the whole thing. All right, so these two matrices are named. What do they look like? So D2 of AB just consists of the diagonal blocks. So you have C of AB and then the nilpotent part. So 0 blocks on the diagonal, 2 by 2 identities, all on the diagonal. But another way we can look at it is, I should give myself more room, but if we look at this not in block form, but just entry by entry, number by number, we have 2 diagonals that are 0s, and then we have 1s up there, and then everything else is 0. Because this 0, this is a 2 by 2 block, so that takes up 2 positions, and then we have our 1s. Okay. Now, so first thing is, we need to know that these two matrices actually commute with one another. So the D2M of AB times M2M and the reason why that works is, what are you doing? If you multiply these in either order, you're multiplying CAB at some point with an identity matrix over here. Well, identity commutes with everything. So I won't go over details on that, but that's the main idea as to why you can show that these matrices actually commute. Okay, so the product in either case is just going to be 0s on the diagonal, and you have CAB up here. Okay. So what happens is, if you multiply with this on the left, it scales every row by CAB. If you multiply the other order, so this first and then this scales every column by CAB. Either way, the result's the same. So, okay, so the reason why we need these to commute is so that the exponential of t times our original Jordan block, which is decomposed in this manner, we can just exponentiate the two individually and then multiply the results. Okay, so that's the exact same thing that happened in the real case. All right. Now, let's deal with exponentiating this part right here. So e to the 2m of AB. So this is block diagonal. So what that means is anytime in a block diagonal matrix you need to exponentiate it, you can just exponentiate the diagonal blocks individually. So I'm just going to have e to the CAB exponentiated all along the diagonal. So now we just have to figure out what are those blocks, these right here, and then we're done with this part, and then we can move on to this. Okay. So okay. Now, we look at CAB. All right, that is A is the diagonal plus or minus B here. So if I'll go ahead and write this as a Taylor series, T to the K, CAB, and the K over K factorial. So we need to figure out what do these powers look like? Is there some pattern? So if I go ahead and square it, so we have A, B, A. Okay. Oh, actually, now I think about it. Well, I'm going to try a different tact here. And make it easier. I'm going to break this down as a diagonal part, the real part, plus the off-diagonal part. Now, but this is just A times the 2 by 2 identity plus this. Okay. Now, these two matrices, do they commute?
Like two commutes with everything.
An identity. Wait, which?
Yeah, that's right. Identity commutes with anything. So yeah, these two pieces commute. So therefore, I can do the same thing I was doing over here in a block case. So I can say e to the t, so instead of using this, that would be too difficult to sort out. That would be e to the t times a times the 2 by 2 identity times e to the t times this off diagonal piece. Okay. Now, if you apply the Taylor series definition of exponential to this, well, that's going to be, this is a diagonal matrix. So, like we've been using already, if you have a diagonal matrix or a block diagonal matrix, use exponentially to diagonal entries individually. So that's just e to the at, 0, 0, e to the at, times the exponential of this. So for this, we want to go ahead and do what I was going to do earlier, the whole thing. Apply the Taylor series definition. So here we can look at taking powers and see what happens. Okay. So if you look at 0b minus b0 squared. Okay. So what's that going to turn out to be?
It'll be negative b squared and the diagonal entry is 0.
Yeah, so the off diagonal entry is going to be 0.
Yeah.
And then
That's
yeah,
also
both.
gonna be negative b squared.
Yeah. Okay. So that's what we have for squared. Now let's look at cubed. So that would be what we just got, the squared, times that. However, this we can abbreviate as minus b squared identity. So there's really no multiplication to carry out at all. It's just going to be basically going to take these entries and multiply them by minus b squared. So we get b minus b cubed plus b cubed, 0, 0. Okay. Now, let's do one more. If we raise this to the 4th power, well, the easiest way to do that is to take this is to the 2nd power, and to square it. So that's going to be b to the 4th. Or actually, I'll just write it element by element. B to the 4th, 0, 0, b to the 4th. Okay. So, what patterns do we see?
Right? And sine and
Yeah.
the diagonal versus off diagonal.
Yeah,
Sorry,
but
not exactly the joke.
even powers are a diagonal matrix with even powers that alternated sign. The odd powers of the matrix are entries only in the off diagonals, only odd powers of B, and again, alternating in sign. So if I were to, so let's take a look at the exponential then. So the exponential of this entire matrix, if I were to combine all this, so we'd have, okay, so we have identity plus this, t plus 1/2, and then we have b squared, 0, 0 minus b squared, t squared, plus 1/3 factorial. Then we have 0 minus b cubed, 0, t cubed, plus 1/4 factorial, b to the 4th, 0, 0, b to the 4th, t to the 4th, and so on. Okay, now, but it'll be easier to see what's going on with the individual entries if we add all of these together and see what's happening with one entry versus another. And then we can see, hopefully you will see a pattern. Well, I'll write out identity as 1, 0, 0, 1, just so you can see how all of this comes together. So if we look at the 1, 1 entry, we only need to look at the even powers. So we have 1 minus bt squared over 2, because notice the powers of b and the powers of t are the same, plus 1 over factorial bt to the 4th, and so on. Okay, so that's the 1, 1 entry. And then the 4, 4, the 2, 2 entry is going to be the same. Okay. Now, the off-diagonal entries, let's see what happens to that. So first for the entry up here, the 1, 2 position. So we have 0, and then I have b, t, okay, minus 4 factorial bt cubed, and so on. And then down here, I have minus bt plus. So these entries are negatives of each other. So I have minus, I'll just factor out the minus. Okay, that's it. Okay, now, do you recognize what these series are? Because you have the exponential Taylor series, except here you only have the even degree terms alternated sign. Here you only have the odd degree terms alternated sign.
Alternating terms. This goes to.
What are these the Taylor series of?
Sine and cosine. No.
Yes.
Yes.
Which one is which?
The cosine
That's
alternates.
cosine along the diagonal.
Yeah, these are cosine, because cosine of 0 is 1,
Right.
and then these are sine. Okay, so what we get is cosine of bt, sine of bt, minus sine of bt, cosine of bt. Okay, which has been abbreviated in the text as R of bt. So this is a rotation matrix. This is clockwise rotation through the angle theta, which is, in this case is bt. So whatever the argument is, that's a rotation in the xy plane.
It becomes counterclockwise if you like change the sign and change the sign cosine are or something like that.
If you move the minus sign up here,
Oh, okay.
it's the inverse.
I know. You told me something like that.
Okay. All right. So now, what that lets us do is we can finish the exponentiation now. So this exponential of this block is, okay, this probably I've worked out already. That's this e to the at identity. And then the exponential of this is rotation matrix with angle bt. So this is what we have here. Right, e to the diagonal block of these complex Jordan forms is that. So now we can just combine that with the exponential of our nilpotent part, and we'd have the exponential of the entire Jordan block. Okay. All right, so now that we have all that worked out, what about the nilpotent part? So before we had, for a real Jordan block case, we had this matrix that has zeros and diagonal, and then ones. So what happened when we squared this matrix? What was the effect of it?
It shifts the ones up.
Yeah, it shifts them up once. So zeros, zeros, and then ones up here. And then if we kept going, it would just keep shifting by one each time.
Until that falls off.
Yeah, until it falls off the edge, so nk to k power 0. Here we have something slightly different. M2m has zeros, zeros, and then ones. So what's going to happen? What's going to happen to this diagonal of ones this time when we square it?
Shift two.
Same thing. No.
Yeah, it's going to shift by 2 this time
Oh,
because it's
it's
2
two
diagonals
now,
over to
yeah.
begin with. Yeah, so we're going to have 1, 2, okay, and then so it's in this position to start with. So yeah, so what that means is this is 2m by 2m matrix, but all we have to do is exponent raise it to the mth power, and it's going to be all 0 because it's hopping by 2 diagonals every time. Okay. So now what that means as far as exponentiating e to the t m2m, it's just going to be a first m term, a term up to the degree m in a Taylor series. So t m2m plus t squared over 2 m2m squared, and so on, all the way down to t to the m minus 1 over, okay, I'm sorry, this is the first m terms. The nth degree term would be 0. Okay, so that's what that looks like. And
What's the size of your matrix? Like, what if every 2 hops? Like, what if can you have an odd number?
well,
Can the size?
it's 2m by 2m.
Okay, never mind then.
Okay, so when we put all this together, we're going to get a similar formula as we did in the real cases. Everything is double in size. So what we're going to get is along the diagonal 2 by 2 identities, and then up above it, it's going to be t times 2 by 2 identities. 2 by 2 identities. And then we'll have above that, so here this is main diagonal plus the first super diagonal. Then this is super diagonals 2 and 3. Then super diagonals 4 and 5 will have the next batch. So that's t squared over 2 times 2 by 2 identities. And as it keeps going, all the way to the end, t to the m minus 1 over m minus 1 factorial 2 by 2 identity. Okay, so that's what happens with this nilpotent part. So now all we have to do to complete the exponential of the Jordan block, of a complex Jordan block, is multiply this by the other exponential that I've circled over there. So but all that's going to do is that's going to take all of these 2 by 2 identities and change them into rotations. Okay, actually, yeah, so because we have e to the dm of d2m, ad is just e to the at on the outside. And then you're just going to have RBT along the block diagonal. So now, in order to get the exponential, oh, there's a t in here. Okay. So in order to get the exponential of t times the whole complex Jordan block, we just have to multiply this exponential by that exponential. So now we can finally put it all together. E to the t C2m of a is e to the at, and what we'll have is rotations down the diagonal, and then t times rotations above that, and then t squared over 2 times the same rotation, and so on, so forth, to t to the m minus 1 over m minus 1 factorial rotation. So that is how you exponentiate a complex Jordan block. So once you have the eigenvalues, the complex eigenvalues, your real part goes out here, then your imaginary part determines the rotation matrix, and you just populate every 2 by 2 block entry with that with the appropriate powers of t over same factorial. So then your exponential of your Jordan form is going to come by combining these with all of your exponentiated real Jordan blocks, and that'll be it. That'll be it. So what I'll do now is, okay, go ahead and do a quick example that combines both real and complex blocks, so you can see, get an idea what the exponential of the Jordan form would look like. Better probably tape it. Yes. Side note, I was thinking of it, since we're getting down to the end, as far as homework submission is concerned, some of you may know from my other class, during finals week, I will only be here on campus Monday and Tuesday. Then I'm off to a conference, and I won't be back until following Monday, which is when grades are due. So after Tuesday, December 8th, if you have any homework left to submit, I'll submit electronically. I don't care if that entails email, or if you want to take pictures of it and text them to me. Some people do that, so I don't care how. But it has to be submitted that way. If you do it on paper, slide it under my door, I'm not going to get it until grades are due. Let's see.
By mail.
Yeah, where's your conference?
Arizona.
Yeah, you suckish. It's Arizona.
Yeah, so not so reliable.
It's taking 4 days to get there.
Okay, let's say by the 12th, preferably, because that will give me some time to look at it on Sunday. I'm going to be visiting a friend during the weekend, so so try not to dump too much on me at that time. Try to get it sooner, and that'll be very helpful, because otherwise it's going to get cranky while I'm grading. Okay, so just keep that in mind. Since our one video student needs to see that as an announcement, Okay, actually I need to move this anyway. Okay, so actually you two submit it like that by that time. Okay, so an example of exponentiating Jordan form. So let's see. I'm going to make a chart of eigenvalues with multiplicities. Okay, so we'll have, let's say, I'll have a real eigenvalue 2 with multiplicity 1, real eigenvalue 3 with multiplicity 3, and then I'll have complex eigenvalues, 3 plus or minus 4i, that have multiplicity 2 each. So we have 4 distinct eigenvalues altogether. So because of a multiplicity, we're going to have 1, 2, 4, 5, 6, 7, 8. We're going to have an 8 by 8 Jordan form altogether. So here's what the Jordan form looks like. All right, so we have 2, that's just 1 by 1 block, not very interesting. And then we have a 3 by 3 Jordan block with 1s. Okay. Actually, I think I need to make this a little bigger. All right, just to do it. Okay, and then for my complex eigenvalues, I'll have 3 down diagonal, 4 minus 4 up here, 4 minus 4 down here. So these are like my CABs on the diagonal. And then up here, I'm going to have a 2 by 2 identity matrix. So the complex Jordan block divides it in favor. So no complex entries, but we do have complex eigenvalues. Okay. So now we can go ahead and exponentiate this. All right, now that lone eigenvalue multiplicity 1, there's nothing interesting there. So that's just going to be e to the 2t. Then, for the next block, a little more interesting, we're going to have e to the 3t all over the place. So e to the 3t down a diagonal. And then down the super diagonal, because of these 1s, what are we going to have up above?
T e to the t.
T what?
T e to the t.
Not e to the t.
Wait. E to
Two.
wait, on which part?
Here. So we're dealing
E
with
to the
these
3t?
one. Yeah, e to the 3t. It's always e to the eigenvalue times t. So t e to the 3t. Okay. And then we have everything is 0 down below. And we have this one last entry up here. What's going to go up there?
Where? Which
Here.
corner?
T squared.
T
E
squared.
to the 3t.
Almost. One piece left.
Over. No.
Over t.
Yeah.
Over 2. Yeah. Don't forget to divide by
I was
the
gonna
4.
say it's the.
So t squared over 2 e to the 3t. Okay. That's the end of that for the real eigenvalue. Now we have the complex eigenvalue. Now, to eliminate a little bit of clutter, I'm going to say that this whole block is multiplied by e to the real part times t, e to the 3t. And we're going to have to divide this into,
But that either 3 still multiply to that block, right?
all of this. Yeah. Okay. So that's the real part. Okay. So that's completely independent of this. These eigenvalues just happen to have the same real parts. Okay. So now, what's going to go in these? Okay. Well, this block is all zeros down here. What's going to go in these guys?
1, 1 in the diagonal.
Well,
No.
it's what I just did.
You said it would be e to the 3t over the diagonals for the reals, right? Took a e to the 3t out.
Yeah, go back to the previous board.
So like cosine of 4t on the diagonal.
Yeah, it's a rotation matrix. Yeah. So cosine 4t, sine 4t, minus sine 4t. Whoops. Cosine 4t. And the same down here. So I should have left more room, but you get the idea. Sine 4t minus sine 4t cosine 4t. Okay, so those are the diagonal blocks. Now if you look again at the previous board, what goes here?
That's our blocks.
So t times
Yeah, t. Yeah, it's this. Well, it's right above the diagonal. So I really don't have room for this. T cosine 4t on the diagonal of this block, and then t sine up here, and minus t sine over here. And that's it. That's everything else is zero. That is the exponential of this Jordan form. Okay. So if I had had more of a multiplicity for 3 plus or minus 4i, I'd have additional blocks down here, and then I have like a t squared over 2 times all this, and upper diagonals. Keep going for as long as necessary, with increasing powers of t over increasing factorials. Okay. Does this make sense to everybody?
So we did all of that and that's just like the final.
Yeah. So now what would happen is, if you have, so for your system, let's say x prime equals ax. Well, that'd be the same as, since your solution, x of t is e to the at x of 0, but that's going to be p e to the jt, p inverse, x of 0. So now you have this piece. But you would still need, I didn't come up with a matrix A for this, just a matrix in Jordan form. But you would need to take your original matrix A, compute its eigenvalues, which would be these here, then compute the eigenvectors,
That'll be the p.
yes, and generalized eigenvectors. In fact, this matrix would be kind of a pain,
Yes.
because you would have to have, you get one eigenvector from here, one eigenvector here, and 2 generalized, and then you'd have 2 eigenvectors here with 2 generalized eigenvectors. So you'd have 4 eigenvectors and 4 generalized eigenvectors to make up your matrix P. But at least this way you'd have a formula for your solution of the entire system. So, because the thing is, for general matrix, computing the exponential is quite a pain. But at least we now have closed form expressions for the exponential of this part. and at least we could break it down into smaller problems. You don't. So now the most painful part of this is not this. It's computing the eigenvectors, especially generalized eigenvectors, to express all of your solutions. And we see, like, from your first DE class, when you solve second order systems, you had cases of real eigenvalues, had what if they're double, like the repeated root, or complex root. And now you can see you got your solutions that have like e to the at and t e to the at, and then e to the at cosine or sine bt. That's where all this comes from. It comes from exponentiating Jordan forms and dealing with repeated eigenvalues and so forth. Okay. All right. Now, wow, I've used a bunch of class time for this, but kind of expected that. Okay. Now, the reason why I'm bringing this up, I mean, we dealt with exponentials before in previous chapters, but what we're looking at for this chapter has to do with fixed points. And is there a way we can conclusively determine whether fixed points are stable, as in they attract nearby integral curves, or are they unstable in that they repulse nearby integral curves? And working with the matrix exponentials helps us to actually answer those questions more easily than we otherwise could. It gives us a good idea of what phase portraits look like. So, so now during the rest of today and continuing on Wednesday, we'll get into stability theory for fixed points. Because what we need in the end is we'd like to have as simple way as possible to determine stability of fixed points. And knowledge of a matrix exponential gives us that simple characterization. Or I should say simpler than the alternative. Okay. And so now, everything I was doing you can see in section 6.2. So now I just backtrack to 6.1, which there's not much in this section, but it's some essential definitions. Okay. Now, okay. Well, let's suppose we have our system. X prime is big X little x. So we're only dealing with autonomous systems here because that's the only time fixed point has any meaning. And C is a fixed point of big X. So in other words, big X of C is 0. Okay. Now, okay. So fixed point is said to be stable if, now there's actually a couple definitions. First, this is the formal definition that the text gives, and that is, in the book, it's phrased as a delta epsilon limit. But what I'm doing here is I'm deciphering all that to be able to state it as an actual limit. So limit as x approaches C of a flow map actually equals C. Okay. Actually, I'll just cut to the simplest form of definition. For all t greater than or equals 0. So what's happening is, notice this limit has a value of t in here. So recall what the flow map means. So this is alpha of t from an integral curve where alpha of 0 is equal to x. Okay. So what is this definition actually saying? That if you have an integral curve starting at x, and x itself, your initial data, is approaching c, that means that the solution for any fixed time is also approaching c. So here's your fixed point c, and here's your initial data x. So what's happening is this is approaching c, but the integral curve that starts at x and goes wherever is also, so this is the integral curve that's also heading towards c. So in other words, if it was an unstable fixed point, and so this condition is not happening, that means that even as x itself is getting closer to c, the integral curve is not. It can actually pull away from c. So C is basically acting like a black hole of sorts. It's sucking everything towards it.
It's for any time t.
Yeah. Now, the actual definition in the textbook just says for t in the maximum interval of existence, except there's a prior theorem that says that if a solution's confined to a compact set, like in a neighborhood of this fixed point, then it's actually defined for all t up to infinity. So there's no point in restricting to an interval, it's just for all t greater than or equal to 0. Okay. Now, so this is a simplest form of a definition that I can give. Bless you. All right. Now, but the thing is, this is happening as x is actually approaching the fixed point. X may still have to be really, really close to the fixed point before you see this behavior actually happening. There's a somewhat stronger form of stability that's called asymptotic stability. And when I write this definition, it might seem like I'm saying exactly the same thing, but I'll give you the distinction after I write it down. So we have a different limit here. If the limit as t goes to infinity of the flow, so notice we're taking the limit of the same thing, except we're taking a different sort of limit. And this is happening for all x such that there's less than delta for some delta.
The flow of x minus c is less than epsilon?
Yeah. Okay, now, we still have the flow approaching c. What is the actual difference here? If you think about, well, I guess you haven't really dealt with, you've done some epsilon k language analysis, but you haven't done delta epsilon stuff, right? Not yet, maybe it's coming. So in the definition of a limit, what's going on here is, for every epsilon greater than 0, there exists a delta, such that if x minus c is less than delta, then this is less than epsilon. So the key here is the delta in question, that's the distance between x and c, is independent of epsilon. So there's an actual ball around c such that once x is within this ball, the solution is going to c. Whereas in the first definition, this is happening for all x such that x minus c is less than delta of epsilon, where epsilon is arbitrarily near 0. So what that means is, here you're choosing epsilon smaller and smaller. That means that delta generally is going to be getting smaller and smaller too. because that's just the way those dependencies all go. But here there's some fixed delta that could be relatively large compared to epsilon, and this is still happening. Okay, so that's why it is possible for a fixed point to be stable and not asymptotically stable. So this is the stronger form right here. So, so for instance, how this would look on a phase portrait is, in the stable case, you need a situation where nearby interval curves are orbiting around the fixed point. They never go away from it, but they orbit it. As that means they aren't necessarily sucked into it either. This just sucks everything in. So, so this is a strong black hole. This is kind of a wussy black hole. It's like, you gotta stay near me, but you don't have to be pulled into me. So, think of it that way. And that's how that actually looks on a phase portrait. Okay. But as you can imagine, checking these definitions is pretty hard to do. First of all, you'd have to have a flow map. What if you can't compute solutions? Especially for a nonlinear system, you may not be able to even have the expression to check if these limits actually hold. Also, you're checking for all x approaching c. X could be approaching c from any direction. Okay, so this is the most general definition of stability. But now we're going to focus on what's actually covered in section 6.2, which is what about stability for linear systems? So that is a lot easier to discuss. And that actually helps us for nonlinear systems. So you guys don't have analysis class after this? Okay, so I'm the holdup. Well, don't worry, I'm still going to end on time. Okay. So now, that was a very brief coverage of 6.1. Now we're back to 6.2, and this is linear stability. So first some definitions. The norm of a vector x is just a regular Euclidean norm. Square root of the sum of squares. Okay. Now, the norm of a matrix is a rather strange one in my opinion, but it's the maximum of the absolute value of Aij for all I and j between 1 and n. So in other words, you just look at the largest entry in a matrix, an absolute value. That absolute value is the norm. Now, both of you, well, actually only 2 of you took 610 with me. When I covered matrix norms, I did not cover this one.
Which one's this?
This is this norm right here. Actually,
What's it called?
Actually, I don't even have a name for it because
Never mind.
I guess if you want to call it the maximum norm,
There's a 2 norm,
And
Frobenius
yeah,
norm.
one norm and 2 norm, infinity norm,
and
Frobenius norm.
Frobenius.
Yeah, and this is not either one of those because, and the reason why this is less useful, I mean, it'll be good enough for our purposes, is that this matrix norm does not satisfy a very important property of matrix norms. It does satisfy the triangle inequality, but the submultiplicative property, the norm of the product should be less than or equal to the sum of the norms, this does not hold for this. So it still meets the other conditions, so we can technically call it a matrix norm. It's a less useful matrix norm because it doesn't satisfy this, but it'll be good enough for our purposes. Okay, so I'm going to use these in order to state these theorems. So for linear stability, we have an easy way of verifying this. Now, probably not going to have time, because I do want to prove one of them, but that is not going to happen today. All right. That's okay. That's what Wednesday is for. Okay, so first, the theorem So suppose your matrix A has eigenvalues now, I'm using this to account for real and complex eigenvalues, just everything. So some of these BJ's, the imaginary parts, are allowed to be 0. But the point is, all of the real parts have to be negative. Okay. Then we have this inequality satisfied, but the norm of e to the matrix exponential is less than or equal to some constant k times e to the minus mt. For t greater or equal to some threshold t naught. Okay, so this inequality holds for some choice of these constants. Okay. And we also have this inequality that follows directly from it, multiplied by vector x. So now this is a vector norm, Euclidean norm. Okay. Okay. That's not a prime or anything, that's a comma. Okay. Now, if we take a look at the second inequality, x is some sort of initial data. What's going to happen then as t goes to infinity? What happens in a
goes to 0.
Yeah, therefore this is also going to go to 0. So what that means is 0 is a season to be sick. Is an asymptotically stable fixed point of the system x prime is equal to ax. All right. Now, all right, I have a couple more results that I'll state, and then I'll stop for today before someone coughs up a lung. Okay. So all negative eigenvalues, or all negative real parts, we have asymptotic stability. That'll help us later for related nonlinear systems. But we also have this instability. So if you have these eigenvalues, and all of the real parts are positive, then we have a lower bound on e to the at times x. And what will happen is, as t goes to infinity, so n is a positive constant, I should mention. Actually, that's true for this previous result, n is a positive constant. So what it means is, t goes to infinity, the solution is going to grow in size. So that means that as t goes to infinity of the solution is infinity. So what that means is 0 is an unstable fixed point. Okay. Now, proving this one is actually one of the homework problems. and they give a hint that if A is all positive eigenvalues, then minus A has all negative real parts of eigenvalues, and therefore this theorem would apply to minus A. So you can use that to help you prove it. Okay, but then here this is a rather weak result about instability. There's a much stronger result. Okay, so this is a corollary to this theorem right here. Whereas we have a separate proposition that's proved in a different way. That says that if it has any eigenvalue that has a positive real part, then 0 is unstable fixed points. Okay. So, because its corollary required all the eigenvalues to have positive real parts. Here, all it takes is 1, really, because what's happening is if you have your initial data, for instance, has any component that has an eigenvector for this eigenvalue positive real part, that part of the solution is going to shoot off to infinity. Even if all the other eigenvalues are negative real part, it doesn't matter. But you had
No, I thought maybe that's the way you define the normal in the matrix, the max of something.
Yeah.
Does that have anything to do with that?
Well, yeah, that's something that you could use as part of it because what happens is t goes to infinity, you're going to have certain entries go to infinity.
Right.
So because what you can do is you can reduce this to its Jordan form, and what happens is in your exponential Jordan form, as we've just seen, you're going to have that one e to the lambda t where lambda is a positive real part, and that part's just going to keep growing and growing. So that growing exponentially, you can actually see in your Jordan form to show that the exponential of the Jordan form goes off to infinity, and therefore the exponential of the whole matrix. So you have a situation like this again. So you actually can prove that. So what I'm going to do on Wednesday to prove this, you can see how similar ideas can be used to prove this. Okay, but since I don't feel like cramming that into, actually I'm completely out of time. It's 4:45, so that made that easy. Okay, let's scram. Okay, so I got through, well, I still have like 5 pages of notes left, but I think we'll definitely be wrapping
Does
on,
that include 6.5?